Hey everyone, we're going to talk about stuff from section 2.1 and 2.2. Finding relative max and mins, finding where the functions increase and decreasing, determining concavity, and finding points of inflection. Alright, so we start with max and mins. We find the critical values. We set the first derivative equal to 0. I get 3x squared minus 12x plus 9. And I can factor this, factor out a 3 out of this expression here. I'm left with x squared minus 4x plus 3. Got a trinomial here, I'm going to factor that. Alright, two numbers that multiply to 3 add up to negative 4. That would be a negative 1 and negative 3. So my two critical values are x equal to 1 and x equal to 3. These are my critical values. That one is not a critical value. This does not have a variable there. But to determine which value is possibly a max or a min, I'm going to do the first derivative test. I'm going to pick some test values and plug it into the first derivative. Determine what's going on with this function. So these are my critical values. Let's see, a value to the left of 1. How about 0? I'm going to test the first derivative at 0. I plug it into the first derivative and I get a positive number. So the first derivative is positive on the interval up to 1. Number between 1 and 3, how about 2? I'll test 2. I plug 2 in here, everyone. I get the first derivative to be a negative value. First derivative is negative at x equal to 2. We're on this interval. And past 3, I get test 4. I plug in 4 into the first derivative expression. First derivative is positive. So what's going on here is the function is increasing. Positive slope. Slope is 0. Function's decreasing. Then the function slope is 0 at x equal to 3. And then the function is increasing. So obviously we have a relative max at x equal to 1 and a relative min at x equal to 3. And I'm going to go fill that in this chart right here. I'm going to put relative max at x equal to 1, relative min at x equal to 3. And everyone, I have to plug these values into the original function. And when I plug a 1 into the original function, I get a relative max value of 5. When I plug a 3 into the original function, I get a relative min of 1. Please note I'm plugging this, substituting it into the original function. Back here, when I was testing values, to determine the first derivative, I was testing values into the first derivative expression. I just want to make that clear. So now we're going to talk about concavity. Where's the function concave up and concave down? And where are the points of inflection, if any exist? And to determine that, you can probably see it from the picture I have here already, we're going to examine the second derivative. So I'm going to erase this. And we're now going to talk about the second derivative. Well, everyone, the first derivative, as you recall, was 3x squared minus 12x plus 9. So the second derivative is 6x minus 12. I'll set this equal to 0. Simply, I get x equal to 2. I am not sure if x equal to 2 is a point of inflection. I have to determine, make sure that the function is changing concavity at x equal to 2. So I'm going to pick some test values again. Number less than 2, how about 0? I test 0 in the second derivative and I get the second derivative negative. That means that when the function is concave down, I'm going to put CD here. F will be concave down when the second derivative is negative. It means the function is somewhat like this on that interval, or takes on those characteristics. Value higher than 2, how about 3? I test 3, the second derivative is positive. That means the function f will be concave up past x equal to 2. So what's going on here with this original rough sketch? I had a relative max of 1, 5, a relative min of 3, 1, and there's a point of inflection in between these at x equal to 2. And then when I plug in x equal to 2 into this original function, I get y equal to 4. And I'm going to label this. This is my POI, my point of inflection. Relative max is 5, occurs at 1. Relative min is actually 1, it's occurring at 3. And here's our sketch. We have our function. Now I'm just going to fill in these spaces from what we have. The function is concave up on 2 to infinity. The function is concave down, negative infinity to 2. Point of inflection, yep, it's at 2, 4. Keep in mind, I substitute the value x equal to 2 into the original function to find this value of 4. Where's the function increasing and decreasing? Back from what we have. We can check this out. What we had earlier with the first derivative, I never filled this in, but the function was increasing from negative infinity to x equal to 1. And again it increases from x equal to 3 to infinity. Function is decreasing on the interval 1, 2, 3. And lastly, everyone, we're going to check this with the calculator. Let's make sure we did this right. So I'm going to pull out the old TI-84. If you got TI-83, that's fine. Y equals, I type it in. I hit graph, everyone, I hit trace. Let's see, let's check out this. I'm going to go to a button, everyone's in the calculate menu, it's above the trace button. And go down this list, go to max, hit enter. It's going to ask 3 questions. First question is left bound. I just need to move the cursor a little bit to the left. That's fine, hit enter. Then ask right bound. I can move the cursor a little bit to the right past that max point. That's fine, I hit enter. I hit enter again when it says guess. The maximum is at x equal to, 0.9999999, that's x equal to 1. 1 comma 5, we're correct there. I'm going to continue to trace. Everyone, let's just check this relative min. Of course, we have a point of inflection right here at 2 comma 4. Go down here, and we're going to check this relative min. Second calc, go to minimum, hit enter. Left bound, move a little left, that's good enough, enter. Right bound, move a little to the right, hit enter. And guess, hit enter. 3 comma 1 is our relative min. It's relative minimum value of 1, and it's current at x equal to 3. And everyone notice it says 0.000005, that's at x equal to 3. That's it.